for the nice introduction, and also thanks to the entire team for organizing this great workshop. I mean, it's always pleasant, you know, to have so many people together interested in the same topics and forming a community. And all these people are from all over the world. That's fantastic, actually. So my talk will be about best practices in topographic analysis and avenues for the development of Topo Toolbox. So what I don't want to imply that I'm doing best practices. I'm, you know, I mean, I can talk a little bit about what's going well and what could be done better. But yeah, let's see what best practices could be. And we are currently hoping to get better, actually. And that's why I will start with a shameless self-promotion here. And that's a job alert. So we are currently seeking for a postdoc and research software engineer in our team. So we have been granted a project to continue working on Topo Toolbox and to developing it further and bringing it to the next level. I will talk about that actually in this talk, and perhaps if anyone is amongst you who think, well, that's exactly what I wanted to do, like doing a postdoc and also getting your feet into the field of research software engineering, perhaps that's the right position for you. Okay, so I guess I'll be talking about what you can expect then in this job, also in this talk. So before we start, actually, I would ask you, because I will do a couple of polls in this presentation here, and I would ask you, you know, either take your smartphone and take a photo of the QR code, or you can also use that link. You can also just enter menti.com and use then this access code. It will bring you to a website that I will use to, you know, to gain feedback and to ask questions as part of this talk. I thought a little bit of interaction is always good, in particular since we are doing everything online here. So if you have done that, let me just change my screen again. And let's go here. Okay, I see the first ones already have answered. So I use software in my research. I mean, I don't expect that there are many who would answer no here, right? I actually was asked this, or I'm just asking these questions, that recently a colleague of mine began a presentation with, and she is a professor for research software engineering, in fact, and so just inspired by that. This one is easy. So still the answers are dropping in, and actually I'm not expecting that anyone would say no here. Okay, but it also makes sure that everyone has the link. And let's see what the chat comes in here. Can somebody copy paste the link there? Okay, thanks. Excellent. But I think we are about, oh, okay, 94 participants. So still a few coming in. And well, it seems like everyone is using software in his or her research. I would be surprised if not. Okay. We can still wait, but I'm going to go to the next one. And so the next one is, software is actually essential for my research. Is that the case for you? Also here, I mean, I would be surprised to find people in a computational geomorphology workshop that don't say that software is essential for their research. So go ahead, click. And well, of course, software is essential for all our research, but it has tremendously increased how that probably has changed in the last 20 years. Okay, I'm going to the next one, because it then says, I actually write software for my research. Is that true? No, that seems to be quite balanced, actually. So, of course, I would expect that in this workshop here, a lot of people write their own software. But still, I think the majority of researchers, in particular geomorphologists, are probably not writing their own software. So definitely we are somewhat biased here. Let me see. Okay, the code is also there in the chat. Okay. So no additional answers coming in. Pretty balanced. So let's go back to my other slides and go here again. So there were these three questions. I use software in my research. Software is essential for my research. I write software for my research. And you know, if you would have asked me like 20 years ago, well, now I'm in research for about 20 years. My answer would have been yes, but I write software for my research. Hell, no, not at all. Well, I had started doing programming, in fact, quite late in my career. I was, during my diploma thesis, I got in contact with MATLAB, mainly because some of the stuff that I wanted to do was just unable to be done using the most common software that I would use before, Excel. And there were no such classes at my university teaching programming. People often thought, well, either you can do it or you can't. So in meteorology, people expected us to be able to code in Fortran, but of course, without ever learning it, that was a hard time. But however, during my diploma thesis, I got very much into programming, or writing code at least, and I actually hang out quite a lot on what is called the MathWorks file exchange. Since I was doing MATLAB, that was a great place actually to learn a lot about coding, about writing software, about writing good functions, and about good practices and bad practices. I also hang out a lot on news groups and so on to read about how people solve problems. And that was actually a very good entry to one of the first things that I actually wanted to solve using software. And that was the following. You know, given a DEM, I wanted to find a way to calculate something that we often need, and that is flow accumulation. So flow accumulation is kind of a special algorithm, I would say, because, well, in the end, every pixel might depend on any pixel in the DEM. Okay, flow accumulation calculates or is based on flow directions. So the directions of flow in each local or at each cell, and then we are trying to determine how these cells add up as the water is transmitted downstream. And well, approaching this, well, I actually had no clue how that would work. I only knew that the algorithms in GIS would take ages to run, and I thought there must be a better way to do that. And so I started digging into that, and I started reading a lot, and I had some rough ideas of how to go forward. And so perhaps some of this, the topics that I had to deal with were topics that reflect very different fields of mathematics, but also the computational sciences, all of which are embraced by geomorphometry and terrain analysis. And I'd like to highlight here in particular, for example, the book by Gilbert Strang on linear algebra, which is really an accessible book for someone like me who didn't have math or not much math in my studies. Then there's also the one from Pierre Soil on morphological image analysis. So what's that? Well, it embraces a lot of techniques from morphological mathematics, which is basically a set of filters, maximum filters and minimum filters, and distance transforms. And that's something that we need a lot. And then, of course, also, but that was not clear at the beginning, graph theory. I mean, it's a German book here, but what I needed was also a bit of an introduction into network analysis and all that. That really took quite a while until I finally came up with an idea of how this could be done, okay? And I just like to briefly show how one of the first, softwares that I developed evolved. And so what you see here is just the idea about how network flows could be represented and how linear algebra would help here. So imagine that you have a DEM, which is shown here, just the pixels, the values in bold are the elevations, and the cells are numbered in a consecutive way from top to bottom, and then it continues in the next column. So this is a linear index running from 1 to 30. So this is a very small DEM of just 30 pixels. And if you show the DEM in 3D, well, that would be a 3D representation of it. Okay, so what was the idea then? Well, I thought it would make sense to store these directions, or to store how the water is distributed locally as a sparse matrix. Okay, so what is shown here is a matrix where all 0 entries are white, and only the non-zero entries are black. So these there are some values in here, could be ones, could be also fractions, which indicate that, for example, pixel number 1, so the linear index 1, drains into or to its neighbors, and neighbor has an index 2, 7, and 8. So that's why we have here in the first row, so the first pixel, some values at the positions 2, 7, and 8. If there's only one downstream neighbor, like for example that pixel 15, then there's of course also just one entry here at that point that we deliver our flow from 15 to 16. And then finally there's also some empty rows, and these empty rows are the outlet pixels that only receive but do not transmit the water any further. Okay, so that was, after a lot of reading and experimenting, one of the first ideas that I thought, well, that's how it might actually work. And that is what is called the transfer matrix, M. And you see that it still exists in Topo Toolbox nowadays as a function which is called flow object to M. So if you need that matrix, that's your function. Now, what is that function good for? So for example, you could derive just a very simple flood routing model. And it's probably the simplest model that you can get. You start with an initial distribution of water. In that case, well, we would have just amount of 1 in every cell. And then we could perform following code. while there is any water left on the grid, well, just multiply the transpose of this transfer matrix times the water available in grid, and just update this grid in the water. So here, just for this purpose, I'm showing here also a graph just in a second, which will be recorded here at that point where this red square is. So we are going to record a run of hydrograph, actually, just, however, assuming that the distance or the speed at each cell is the same. So when we do that, well, our hydrograph would look like that. It will drop, it will rise again a little bit, and then after some time, the entire flood wave has passed, and we're gaining, again, zero discharge, okay? I was actually recently asked in one of the GitHub discussions whether this can be done, and then I remember that I had done this like a couple of years back. And so it's actually quite fast. It's a very simple run of model, as I said. However, that doesn't give me flow accumulation. Okay, so what is flow accumulation then? Now, that's the only math that I'm going to show. But in the end, flow accumulation is the integral for every point or for any location below the hydrograph. Okay, so summing up actually all these values would give you the number of pixels draining through each grid. And so that's the water amount at the beginning plus the water amount after the first step, water amount after the second, and so forth after n steps. Well, it takes a little bit of math, including, again, transfer matrix. Okay, and what it boils down to in the end is an infinite geometrical series, which then can be solved using linear algebra. So in fact, we can express that infinite geometric progression as the inverse of one, or the identity matrix minus this transfer matrix, and so forth. So that was, for me, an extreme eye-opener. And actually, I didn't come up with that just alone. It was with the help of people on the MathWorks file exchange and news group who actually guided me to this solution. And that is just what I would call just a flow accumulation equation. The good thing is, well, you can do with it all sorts of things. You can route all sorts of material downstream, and you can also route things upstream. So it's actually, for drainage basin delineation, it's basically the same equation. Okay, so the linear system of equations describes the steady state discharge in each cell for a given input of W0, so the initial water. So, and well, that was also then the time when I started writing my own software. And in fact, this equation and the way how we get there is implemented in a function that I wrote before Topo Toolbox was actually initiated or born. It's called WFlowAC or WFlowAC. Somehow I thought it would be good to have the initial of my first name in front of the function name. And it's still available on the file exchange. But let's see, I want to show you something. So I'm switching here just to MATLAB. I hope you can see MATLAB now. And I downloaded that function again as it's still there. And I thought, come on, let's test it, whether it still runs. So what I'm doing here, I'm just using, first of all, Topo Toolbox to read a grid and so on, but then I cast it to some matrices that I am using for that function. Okay, so in fact, X, Y, Z, 3 matrices, one matrix with the X coordinates, one matrix with the Y coordinates, and one matrix with elevation values. Okay, then I also needed to fill the things. There's a function in MATLAB that does it. It's called infill. So this is already a filled set elevation grid. And so now let's run the old flow arc. And we do that, and TikTok measures the time, how long it takes. Okay, we still need to wait a little bit, but there it is, 10 seconds. So for a pixel size, or for a DM size of 1,000 times 600 something, actually quite slow, but it worked. It was faster than any GIS that I would know at that time, at least ArcGIS. It would, at the same time, derive flow directions and flow accumulations. Now, nowadays, that's a bit faster. Okay, just takes 0.5 seconds. So after a while, we sped up or speeded up this process. But we come to that at a later point. Nevertheless, the software that I wrote, so that's the first piece of software that I wrote. And actually, looking at it after, it was actually written in 2009. At that time, I was in Basel still. And yeah, it had a H1 line, so it could be found by the function look for in MATLAB. That's what I learned by talking or by communicating to other developers. It had a documentation that was a bit similar to those documentations that MATLAB provided. So input arguments, output arguments, and providing an example. Required XM files, and then code, which is also quite commented. So it wasn't actually that bad. Okay, going back here. So that was actually the birth then of Topper Toolbox 1. We published that in Environmental Modeling and Software at that time, first available in 2009. And yeah, it was reliant on MATLAB 2009A, and yeah, it was free of charge and could be downloaded. Drawback, it was still relatively slow. There was no use of any coordinate reference systems, for example. And in fact, a quite cumbersome syntax of function calls. Why? Well, there were always these X, Y, and Z matrices, and perhaps even some more stuff that had to be delivered from one function to the next one. What we didn't have at that time is no versioning, no software versioning where we could get some control about the development. Testing, well, if the function runs, that's great. There was not even a permanent software link. Okay, that one doesn't exist anymore. It's already broken. And there was also no proper documentation. So still, Top Toolbox started to be used by others, which is kind of a motivation. And so I would call that, however, my first piece then of research software. Okay, let's go back to our slide here. What do you think? What is special about research software? Now, this will generate a point cloud. So I think you can enter up to 3 different terms that you would say, what is actually special about research software? So I'm looking forward to seeing how the point cloud evolves, and I hope it does that while we are writing. Okay, documentation, adaptability, extendable. Yeah, never finished. Reproducibility, yes. Oh, I love that tool. Speed should be fast. It should be open source, yes. Okay. reusable, easy access. And I've seen some were frustrating. It can be frustrating, yes. Quantitative, never finished, tailored. Free, yes. Provide missing tools, yes. Should be for specialists, exactly. Okay, it's still evolving. 142, 143 responses. Batch process is a unique solution. Should be rigorous. Complex. Okay, I think we're getting to some final solution. Thanks for providing all these. It's a time saver. Yeah, I hope so. That's some research software. I'm not sure whether it's a time saver, but okay, I think we should have a screenshot of that. So thanks. There is a lot of terms that are definitely associated with research software. Let me go back to my slides. Okay, so what is actually special about research software? There are a lot of terms that you used that are actually also used by others who do that professionally and saying what is actually research software. It's a kind of new field in the computational sciences. And as you said, it's often highly specialized. It's for specialists. It's indefinite in terms of development times. It's rarely finalized. There are frequent changes. It should be reproducible, or it should, let's say, foster reproducibility. So it has high requirements regarding transparency, reproducibility. There are often perhaps some discipline-specific quality criteria that should be met. Rarely, and that was also the case for me, there are professional software developers. Often research software is developed by people who have not much experience in developing software, that have not had training to do that. And yeah, finally, often you have very diverse and alternating teams that develop software. So in many respects, this first version of Topo Toolbox met many of these criteria, except one, and that was diverse and alternating teams, because it was still something that I mainly did alone, actually not with help of many others. And looking at other projects, like, for example, LSD Topo Tools, I mean, a lot of people contributed to that. Or when I think of the Greg Tuckers and colleagues, LandLab, for example. But those are typical for where you have diverse and probably alternating teams. Okay, so when I moved then to Potsdam, I started collaborating with Dirk Scherler. And we came up then with the idea, okay, let's develop Topo Toolbox 2, but because we saw really some drawbacks in Topo Toolbox 1 and had some ideas about how to proceed and to refurbish or to renew this software. And that came with a couple of innovations. So first of all, we developed a couple of numerical objects, adopted techniques from object-oriented programming. And what we wanted to have are actually objects that are more familiar to geomorphologists, hydrologists, geoscientists, structural geologists, whomever. So instead of having these individual matrices that you would input to functions, there should be more understandable objects. There should be techniques from network analysis and graph theory. And in fact, we had luck with some design decisions that we made. I'm not sure whether they were intended at the beginning, but in the end, they proved to be quite good. And then also collaboration started. So in that case, we developed TTLEM together with Benjamin Campos, who's perhaps here also. And we also thought about, well, let's focus on workflows. How do actually people use that software, and what what might be possible scenarios how they use it. And in the end, we also started writing the Topper Toolbox blog, which was more a fun project at the beginning, but I think was very crucial for keeping the software alive and to attract a large user community. So how does Topper Toolbox 2 now work? Now, I said we introduced the numeric classes, and in fact, first of all, these classes are quite simple. The first one is a grid object. Again, okay, grid object is kind of a weird class name, but I thought, well, it's an object, so let's give it an abbreviation OBJ at the end. I think I wouldn't do that again, but okay. A grid object, which is a DEM or any other single band raster. And well, it stores the grid, it stores the projection and georeferencing. And potentially it could also store units, for example, or a name of that grid. And well, it was actually just constructed from a file, TIFF file, ASCII file, or TXT file. And actually that is still the case. You will need to update that soon. From this grid object, you would be able to construct a flow object, which stores the flow direction. So something which is actually very similar to this transfer matrix that I introduced before, but here we used a more clever way to do that. And in fact, that involved what is called topological sorting. Now, going a bit back to mathematics, the system of equations that is being solved with the transfer matrix is actually a very simple one. So it can be, by permutation, be cast into an upper triangular or lower triangular system, which can be solved very quickly. And why is that the case? Well, because we have a directed acyclic network. And actually, this permutation can be computed with either a Dulwich-Mendelssohn permutation. Somehow I stumbled across this kind of permutation and found out, well, it does exactly what I need. But later on, I also realized that it's actually the same is done using what is called topological sorting. So what does topological sorting do? Well, it sorts the list of indices into a way that each pixel in that list doesn't have any upstream neighbor below it. So meaning we could start here with a 7. We know that it's draining to 2. That one is 1 also to 2 and so on. So all these here need to come in a list before the 2 and so forth. And we can actually do that for each drainage basin. We could do that even individually and parallelize some of these equations. This gives us a sorted edge list. Again, what is a sorted edge list? Well, we know, for example, that the 7 goes to 2, so that's from IX to IXC. So it's this downstream neighbor here, goes from 7 to 2, and that's our first edge in that list. Because, well, there's no edge upstream. Then there's the 1 which goes to 2 and so forth. And so we get this topologically sorted edge list, which then can be used to really quickly calculate flow-related terrain attributes. And in fact, what meant like solving an entire system of equations in Topper Toolbox 1 boiled down to just these 4 lines, basically. So you initiate a matrix of ones as the initial amount of water, and then you can just run through this edge list, involves some awkward indexing and so forth, but that goes super fast. And so the algorithm turned out to be big O(n) in the end, okay? So scale just linearly with the EM size. Okay, so that is what is actually stored and retrieved in the flow object. And based on this flow object, there was a stream object. Since, well, in tectonic geomorphology, a lot of people are interested in, how river systems store tectonic information. And so stream object is actually a flow object reduced, so a subset of the flow object, but it also has the same network structure as the flow object. Okay, and then there was another object, swath object, but let's continue. So in fact, these different objects can be looked at kind of linearly. We have a grid object, a flow object, and then a stream object. But in fact, they interact. And that's how we started to think about workflows. Okay, so we have a grid that we start with, we derive flow accumulations, we delineate the stream network, but for example, based on the stream network, again, we can calculate the distance to the stream network, which gives us a grid object again. So all of these objects start to interact with each other. And this interaction is basically is the basis for workflows that would be possible with that approach. So, and in fact, over the time, these numeric classes grew in functionality, and so we added a couple of classes. So, for example, one divide object is one that Dirk developed, and it stores actually divides, something that you wouldn't have in the other stuff you would have in GIS also. But a divide object is something that is not in any GIS implemented, but is quite natural in a way how we think of landscapes. The same goes true for PPS. I think it's not used a lot so far, but it means point patterns on stream networks. So since I'm also doing a lot on spatial statistics, that was something that I wanted to develop, and which means point pattern analysis, where the points are actually attached to streams. And what could that be? What kind of phenomena could be addressed with that? Well, for example, the location of landslide dams, the location of beaver dams, riffle pool sequences, and stuff like this, where you have individual locations, events, whatever, which are attached to a network. And so PPS provides these tools to do this and to do analysis with these kinds of data. So then also, I said that we developed the Topo Toolbox landscape evolution model. And that was something that was spearheaded by Benjamin. Now, the animation that I will show shortly has been now done with a still unpublished version of TTLAM. I mean, it's just lying around there for, let's say, for more than a year now. What is different to the initial TTLAM is that it handles layers of lithology. And so what we are seeing here is a plane view from above, bird's eye view on a DEM. And here we have a cross section taken from the left lower corner to the right upper corner, and which shows some alternating layers of different rock hardness. And I think the hard rock is the dark one, and the soft one is the yellow, light one. So, and when we run that, gives quite some intriguing patterns here. How, if you have some dome uplift in that case, how that would be modeled here. This view here is unfortunately not so, I think, can not very well be seen. We only see how the different layers appear at the surface and then form these concentric circles around the center of uplift. I think it can be better seen here in that figure, where this is kind of mesmerizing, that you see how these landscapes of dome uplift develop. And that is something that I'm currently continuing working on with Maximilian Raum, I think, who is also here listening. So this pulsing things, that's basically when new bedrock layers come to the surface. Okay, so Topo Toolbox now with version 2 seem to have evolved also, and I think it also approached something which has been recently introduced as the so-called FAIR principles of research software. So what does that mean, FAIR? Well, it should be research software, to follow the FAIR principles, should be findable, accessible, interoperable, and reusable. Okay, and there are 5 criteria that could be taken here. For example, it should be openly available. It should have a license with it. It should be registered. For example, it should have a DOI. And by having a DOI, it should be citable. And there should also be quality control. So, for example, that the software is verified, that there is testing, for example, by X-unit tests. So did we, or do we have that with Topo Toolbox 2? Openly available? Yes, of course. I would say Topo Toolbox is perfectly open source, but unfortunately the software that it relies on is not. So currently it's still dependent on MATLAB, and users require a MATLAB license, and not only a MATLAB license, but also a couple of toolboxes to have the full breadth of tools available in Topo Toolbox. So for example, you need the mapping toolbox, you need the image processing toolbox, and it's good to have the parallel processing toolbox and the statistics and machine learning toolbox, and perhaps also the optimization toolbox. And then it becomes very expensive, actually, and quite prohibitive for people in low-income countries to use, at least legally, Topo Toolbox. Is there a license? Yes, but actually I looked it up, didn't find one. There should be a GNU license, but actually it's not something that we thought really through, right? It's not really thought out well what kind of license model Topo Toolbox follows, something that we need to do. Is it registered? Yes, the paper, there is a paper about it, the 2014 eSurf paper, and some Zenodo repository. It's citable. Yes, the main paper and several methods, tools, and papers exist. So in that case, it's citable, and I'm glad to see that it's also cited a lot. And finally, quality checklist. No, we don't have that. There is no testing. Bugs might show up. If they do, we correct for them as best as possible. But many of these tools that we develop don't lend themselves, let's say, for real testing. So because often there is no, what is the true solution then? Of course, for some stuff there is true solutions, but it's not like comparing a numerical algorithm with an analytical version. For some special cases. That's actually not done here. And so we thought, okay, the Topo Toolbox is not really, there's room for improvement, let's say. And that's when I want to come to avenues for further development. So seeing these drawbacks, we thought that we are going to submit a project proposal to the German Research Foundation, the DFG, and we did that in January 2023. And happy to announce, since since 2-3 weeks, I know that this project has been funded, and that's why you had this job advertisement also at the beginning. Now, what are we going to plan? And that is, first of all, well, Topo Toolbox was developed by just Dirk and me and a couple of others also. Some minor contributions, but also some big contributions like TTLAM. But it's not really a community effort. I would like to see in the future that Topo Toolbox becomes more a community effort. And so one idea is really to involve the community more, and that's why I'm particularly happy to announce that here and to welcome you to get involved and to stay tuned for more information about that. One big thing is also to recode the core and port the application layer to other languages. I'll talk about that in a second. And then there is some additional goals like big data. Julia talked about that. So enabling analysis of huge DMs and then also spherical geometries. So let me just talk about that briefly. What means to recode the core? So in fact, there is some computational core, and actually it's like the derivation of flow object, which has been there for years, and I actually haven't touched that much anymore. So that core is quite stable, I would say. But of course, it's currently relying a lot on these MATLAB functions provided by the image processing toolbox. And that makes it difficult to port that code to other languages. These functions are flood filling. There are some functions that need to do distance transforms and topological sorting. Okay, and the idea would be to develop a core, a numeric core in C or C++, and that is what a research software engineer and our collaboration with the computational scientists who are involved in that project would be dealing with. And I've put also here Boris. I'm not sure whether Boris is around here, but we have some ongoing collaboration, and I hope for his input also here, because I'm actually not a C or C++ programmer. So that would provide the core, and then building on that core, we would have that application layer, which actually exists in MATLAB nowadays, and ideally, nothing would change for those using MATLAB. So preferably, there would be no syntax changes, which means total backward compatibility. However, we would require, of course, or what would be nice to apply that core also in other programming languages and to create bindings in Python and in R. For example, interfacing with NumPy in R, you could use stars, Terra, or SF. In MATLAB, it's the mapping toolbox, to actually then also implement tools like Nick Point Finder, chi-transformation, and any plotting routines in these respective programming languages. And that is something that we can't do on our own. Here, collaboration with the community is needed. And so our aim is to activate actually this community, who was actually you. But first of all, the challenge. Now, when saying, well, we are going to code a core, well, that means that a lot of stuff needs to be written, and there is we are making a trade-off between, first of all, reinventing the wheel, because most of these tools have already been written, like topological sorting and so forth. So we might reinvent the wheel here and then, but we also need to balance this against becoming vulnerable to breaking dependencies. But I like that figure here quite much. So all modern infrastructure, and then a project some random person in Nebraska has been thanklessly maintaining since 2003. So this could be GDAL or something like this, which is that little thing here. And if that would not be continued to be developed further, then the whole building of infrastructure, of digital infrastructure, would collapse. And we would like to avoid that collapse. And that brings me now again to the last question here. Let's go back to the Mentimeter and go to the last question. So in your sense, what would you do as a software developer? You see that this is a kind of risk strategy. When we write the core, it could mean that we are reinventing the wheel. On the other hand, if we don't, and when we rely on a lot of dependencies, we run into the risk of software collapse. Let's say if some of these dependencies break, and some of them might be crucial. So now up to you. What would you do? Like, of course, harsher thing, don't accept software dependencies unless they have a very good track record for stability. Or make your software solid enough to withstand typical dependency clashes in your area with a safety margin. When dependencies may fail, do repair work before collapse happens. Or accept that your software is short-lived in case of collapse, start from scratch. I love these animations. So it seems, I mean, there's definitely a modal value so far, which would say, okay, yes, some dependencies are okay, but clearly introduce a safety margin. In the meantime, I'm looking into the chat, whether there is anything that I haven't seen. Okay. Then there are already some questions coming in, which I won't look at right now, but later on. Okay, so I think you have spoken, and most of you would say, make your software solid enough to withstand typical dependency clashes in your area with a safety margin. Okay, whatever that actually means, what that safety margin, I have no idea how I could actually implement that. Except that your software is short-lived. Yes, I mean, that's an option. And now all these choices are actually not, it's not some which I invented, going back here, but were actually nicely introduced by Hinson in his paper dealing with software collapse, computing in science and engineering. And so I've rephrased them a little bit. I like actually the way how Hinson phrases them in a way that it's about, as if it was about seismology. So avoid risk at all costs, build on stable foundations only. Don't build a house in a zone with seismic activity. Don't accept software dependencies unless they have a very good track record for stability. Or 2, make your construction robust. Make your house solid enough to withstand typical seismic activity in your area with a safety margin. When shaking foundations cause damage, do repair work before collapse happens, or accept that your construction is short-lived in case of collapse, start from scratch. So most of you basically said, okay, it's 2. Now the question, what to do, is actually, I would say, it's a timescale of the software, right? If you are having a software project, which is really just for a project, so with a short time period, I think it's totally fine to depend on a lot of different software, because it doesn't matter if it will collapse in 1 year or 2 years. Now, Topo Toolbox lives now for more than 10 years, and I hope it will have another decade ahead. So I think our strategy, it's not completely sorted out yet, will go into either 1 or 2. So really, and that's a good justification for actually writing a core ourselves, which we can maintain. It's actually also a strategy that has been adopted by other developers of terrain analysis software. So for example, John Lindsay, who developed the white box tools. I mean, he programmed basically everything by himself, and this stuff runs in a very stable way. Involving the community. So far, TT was developed and maintained mainly by 2 researchers with contributions from few. It would be nice if we had more involvement, and that's in particular required if Topo Toolbox shall exist in other programming languages. However, we don't only want other programmers. There's another involvement possible, for example, in documentation, perhaps in parts in importing, which is, well, you need to have some experience in programming, but rewriting code in other software is not so terribly difficult. Testing, or perhaps we are actually considering whether a book project would be a nice community effort for the future. And possible actions to attain that. So we are planning a hackathon in the near future, courses at conferences, and perhaps also online workshops. Finally, I'm not going to talk about that a lot, but it was mentioned also before, big data and spherical geometries. I mean, we need to keep up with all the trends, well, not with all, but with the main trends. And what we see here definitely is an increase in spatial resolution and an increase in memory requirements. Topo Toolbox keeps everything in memory, in main memory. So it's a bit limited by the RAM that you have available, but theoretically, it also stops working as soon as you have more than 65,000 something squared pixels. Okay, so imagine you have a DEM with that many rows and that many columns. That's the maximum thing you can do. But actually, it doesn't work so well here anymore. Basically, first of all, you have a very high memory requirement just to store that DEM, and then intermediate products will need that as well. So I'm currently running up to 20 to 30,000 rows and columns DEMs with Topo Toolbox. That's possible. Spatial resolution will increase, and there are good ways to handle that. So for example, looking at the works from Richard Barnes, these are things that we could implement, and we are trying to do. Another thing of development could be the development of that Topo Toolbox works with spherical geometries. So in particular for large-scale applications on Earth and other planets, we might actually be better off with spherical geometries. And it's actually possible to do that. It requires quite some work. For flow-related algorithms, it's pretty straightforward, I would say. But for example, other stuff like convolutions, they need to be adapted to these geometries. And so that's a challenging work that might be something, or for somebody who wants to do this postdoc in our group. I'd like to come to the end. Oh, I think I'm already far too long. So what makes terrain analysis software useful and successful? Well, it's good if it has a low barrier access, intuitive workflows and a documentation, and comment your code. What makes code bad? No comment, okay? It should be robust, user aware, and at best have few bugs. And what makes the software then finally endure over a year, and like Topo Toolbox did? It should be open. I hope we gain some community involvement. It should be tested under constant development. And well, I thought this blog writing stuff that I did with the Topo Toolbox blog was already quite helpful. Sorry for taking so much time. I think I was longer than I expected. Thanks for listening.
Thanks, Wolfgang. That's great. So we have maybe 5 minutes for a few questions. I'm just going to open up our Q&A and we'll see what people are asking. So one question that we've got, so there's a few kind of technical questions that maybe you can answer in the chat rather than us discussing. But could you maybe talk a little bit about the challenge of writing software on top of MATLAB, where you have no control over MathWorks changing things underneath you? Like, has that been a problem in the last 10 years?
Strangely not. So that's why I was quite surprised that the old function from 2009 still perfectly ran. Okay. So I think that MathWorks tries to maintain as much as backward compatibility as possible. However, some of the stuff might be deprecated after a while. So we are making some of these changes. And one major change, for example, was in 2014 that MATLAB switched to a new graphic system. And that meant that we had to change a GUI Topo app, which existed in Topo Toolbox. And then we thought, okay, no one's using it anyway, let's kick it out. So yes, there is that problem, but I think it's not there to a degree that it would be in other languages, like in R, for example. So my experience in R is that a lot of functions tend not to work anymore that used to work like 5 years ago.
Yeah. Okay. And I'm gonna be cheeky, and I'm gonna ask a question that I'm curious about. So looking at the way that you developed Topo Toolbox to begin with back in kind of 2009, compared to your plans for the future, do you think it's possible for one researcher to develop something that is so useful and so important for the community, or does it now need to be much more of a community effort because things are more complex and more challenging now?
Well, it's on the one hand, it's also easy to work alone, right? It's of course you can do some design decisions, but you don't need to discuss them with anyone. So you can be quite fast if you have the time. Now I'm getting increasingly less time, and that's to a lot of teaching obligations. So I think I wouldn't be able to do that anymore nowadays. But in the end, this Topo Toolbox development didn't have anything to do with my PhD, so it was just something that evolved during that time and just by the fascination. However, something of that scale, I think in the end it would be more fun to have a community and doing that jointly. And because if you do that, you also find bugs better. You can better you exchange. I was a lot alone at that time. No, just joking, but I was not communicating much about that stuff actually. Yeah.
Sure. Okay. And I think the other questions that we have, so someone who was preempting you announcing the plans to maybe shift some things to Python. So clearly there is an appetite for that. Someone else talking about the use of Octave as a replacement for MATLAB. I don't know if you have any experience with Topo Toolbox and MATLAB. And Octave, excuse me.
Yeah, so there are two alternatives actually, Octave and Scilab. I think Octave is the more mature one. I've never used them, but I think it should be portable. But there's some, the stuff from the mapping toolbox, and so I think there's no such equivalent in the Octave distribution. So there might be difficulties, but
yeah. I mean, I think
should try out. I didn't have the chance to do it so far.
Yeah, and I guess, as you're saying, opening things up to a community then lets you explore a lot more avenues because there's more people doing things. Yeah. Okay, wonderful. So I think we'll leave it there for questions so that everyone can take a coffee break.